Welcome to all of you. We are so pleased to have you joining us today at this webinar, which is proudly brought to you by the Minnesota Water Research Fund. Thanks for taking time in your busy Monday to join us. My name is Shannon Walkerstorfer. I work in external relations here in the College of Science and Engineering, and I'm fortunate to work closely with our college's alumni, our industry partners, and our benefactors. I'm also really proud to be a member of the Advisory Committee for Minnesota Water Research Fund, and I look forward to having you hear from our founder and chair, Bernie Bullard, in just a moment. Before we get started, we're just going to do a couple of Zoom-related housekeeping items to make sure that our webinar runs smoothly. First of all, if you'd like to listen to today's webinar by phone, feel free to dial in using the information you can find on your screen right now. Of course, we welcome you to submit questions throughout today's webinar. There's going to be a bunch of great research information shared, and so we want you to have an opportunity to use that Q&A feature at the bottom of your screen to submit your questions. We will get to as many as we possibly can during our Q&A session after the presentation. If you have any technical issues, we'd like you to use the chat function. I have a colleague standing by to help you with that, so just go ahead and put a note in the chat to her. As you see on the screen, we are indeed recording this presentation, and we will share the video recording with you in a week or two. And finally, if you need it, we do have the live auto transcript feature enabled for this webinar. Just go ahead and click on the live auto transcript feature at the bottom of your screen to either show this or to hide this. Now that all that housekeeping is out of the way, it is my pleasure to introduce you to our founder and chair of the Minnesota Water Research Fund, Bernie Bullard. Bernie has devoted the better part of his life to ensuring that our water is safe. We're so proud to call him a University of Minnesota alumnus. Bernie has both his civil engineering degree and his master's in business administration from our university. And he is a well-known leader in the regional and national water and wastewater engineering field. Over his career, Bernie led St. Paul Regional Water Services, was director of water treatment and distribution for the city of Minneapolis, and he shared his many talents with local firms like TKDA, SL Circo, and CDM Smith. He's also been an active volunteer with organizations such as AWWA, APWA, and many more. Bernie has incredible expertise, and his expertise is matched only by his unstoppable commitment to ensure that effective management of our water supply is informed by sound research. He has a vision to have Minnesota continue to be a leader in this area. And this is why he founded, with his own personal generosity, the Minnesota Water Research Fund in 2015. I'm pleased to turn things over to Bernie now to share more about what inspired him to create the Minnesota Water Research Fund. Take it away, Bernie.
Thank you, Shannon. And thank you all for joining us today for the 5th research webinar hosted by our Minnesota Water Research Fund. Because one of our important goals is to communicate and share water research news with a broader community, it is thrilling to see that today's webinar has generated interest from more than 400 people. I have spent my life and career as an engineer focused on water. That's why I created this Water Research Fund at my home university, the University of Minnesota. As a student, I worked part-time for 3 years in water research, either at St. Anthony Falls and partly at the Civil Environmental Lab in the Civil Building. And I enjoyed working in water research. And as a manager at St. Paul and later Minneapolis, I hired the university to help me with water research related to upgrading the water filters at both water plants. Water research has an essential role to play in the future of our cities, states, and our nation. We cannot allow our technologies, knowledge, or management practices to become outdated. Research is vital to ensuring access to clean water for this next century. The philanthropically supported Water Research Fund currently funds faculty and student water research in the Department of Civil, Environmental, and Geoengineering here at the CSE. Our vision is to enable the university to be a nationwide leader in innovative water research to improve public health and protect Minnesota's water resources. The fund's short-term goal is to provide annual research grants for faculty and students working in water treatment and water research management. And our long-term goal is to raise $2 million to create an endowed chair to support the U of M faculty member who is an international leader in the field. We're already making an impact. In just 5 years, the Minnesota Water Research Fund has supported 8 projects led by CSE engineering faculty working with graduate and undergraduate students. We have also supported the purchase of vital research equipment. Our past projects are summarized on our website. So we've done several projects, and if you want to look back at our history, they should be on our website. And if you wanted to review any of the previous presentations, just let us know and we can arrange that too. In our most recent round of awards, our fund chose to support the exciting stormwater research being conducted by today's presenters, Professor Emeritus John Gulliver and PhD candidate Vinita Gupta. We also regularly host research webinars like this one to introduce a broader audience of alumni, water industry leaders, and external stakeholders to the water research happening at the university. For more information on our fund, please visit our website. At this time, I'd like to take a moment to thank and recognize the volunteer members of our Minnesota Water Research Fund Advisory Committee, which is composed of U of M alumni and water industry leaders whose names are listed on your screen. Dave, Lisa, Tricia, Bo, Andrew, Naeem, Michelle, Carl, and Stu, thank you for lending your time and expertise to help us expand the reach and impact of our Water Research Fund. I'd like to now turn things over to Professor and Head of the Department of Civil, Environmental, and Geoengineering, Paige Novak. Paige is the Joseph T. and Rose S. Ling Chair in Environmental Engineering. After running a robust research program and teaching and mentoring students in the department for nearly 25 years, Professor Novak also took on the role of department head this year. Her area of research focus is the biological transformation of hazardous substances into sediment, groundwater, and wastewater, resource recovery, and particularly how engineers can influence these processes. Please help me welcome Professor Paige Novak. There you go, Paige.
Thank you, Bernie. It's such a pleasure to be joining everyone here for this 5th virtual event hosted by the Minnesota Research Fund. And it's great to see so many participants joining us as well. It's a record crowd. Bernie and the Minnesota Water Research Fund committee members, I would like to thank you on behalf of the university and also on behalf of our department for your hard work and your dedication to ensuring the university can be a worldwide leader in innovative water research. In the Department of Civil, Environmental, and Geoengineering, our vision is inspired and innovative engineering for society. This vision is put into practice through the expertise of our faculty and in the excellence of our educational experience that we provide our students. These students are the engineers and scientists who will be in charge of tackling important grand challenges and also managing and protecting our water resources in the future. Our environmental engineering program is ranked 11th in the country by the US News and World Reports. We have a great tradition here of excellence, and we're excited to continue this tradition with the help of our committed faculty, students, and alumni, such as Bernie. We're really honored to have the partnership of the Minnesota Water Research Fund and its advisory committee, many of whom are alumni of the department. And it's important to note that in these resource-constrained times, securing water research funding at local and national levels is an increasing challenge. This fund that Bernie established helps our department tackle current and emerging water quality problems by supporting University of Minnesota faculty and students working in water resources management and water treatment. A lot of this research helps guide critical water infrastructure decisions and investments across the state of Minnesota, and it improves public health. As Bernie mentioned, this work funds research that, or the fund funds research that has been actually implemented at our water treatment plants in the area. The fund also helps provide top-notch education and research experiences for our students. Finally, this fund is offered early stage funding for novel water research, which may not have been able to get funding otherwise. And in multiple cases, this initial seed funding has led to additional funding that's been able to advance this research to a point where it can be deployed or used to support state decision-making. So with that, it's now my pleasure to introduce you to our first presenter, John Gulliver, who is likely a familiar face to many of you. John Gulliver is a professor emeritus in the Department of Civil, Environmental, and Geoengineering, and he's also a resident fellow at the University of Minnesota's Institute on the Environment. John received a BS in Chemical Engineering from the University of California, Santa Barbara, and an MS and PhD degree right here from Civil Engineering at the University of Minnesota. During his more than 40 years as a faculty member in the department, John has taught courses, in fluid mechanics, environmental mass transport, and urban hydrology and water quality. Much of John's research, in conjunction with other faculty, involves the development of new technology for the treatment of road runoff and assessment of field performance of stormwater treatment practices, including the SAFL-BAFL, which converts any sump into an effective sediment settling device and has been deployed nationwide. He's also developed the iron enhanced sand filter, which removes dissolved as well as particulate phosphorus, and the MPD infiltrometer, which can measure infiltration into soil accurately and effectively with a minimal volume of water. He is a co-author of the book, Optimizing Stormwater Practices, a handbook of assessment and maintenance, which has been published by Springer. So with that, I will turn it over to John.
Thank you, Paige. I would like to discuss another aspect of what the Water Research Fund means to graduate student research at the University of Minnesota. A difficult problem that most graduate students encounter is finishing their thesis and receiving funding to do so after the project is finished. Typically, project report and the project are complete, but the thesis is different from the project report and still needs to be completed. So the Water Research Fund comes in and allows a student to finish their research and their thesis under funding. So I'd like to give a heartfelt thank you to the Water Research Fund and Bernie Bullard for their efforts on the students' behalf. So now I would like to introduce one student for which this is true. Vinita Gupta is finishing his PhD thesis under the Water Research Fund. The title of the talk on his thesis topic is, Do Stormwater Ponds Improve Water Quality? So I give you Vinita Gupta.
Thank you, John. I'm extremely grateful to be, as John mentioned, receiving this gracious funding to allow me to finish up and nicely package all of the hard work that we've been doing for the past couple of years. It certainly is a difficult, as John mentioned. So without further ado, I'm going to be talking about whether stormwater ponds improve water quality. So John Gulliver is one of my advisors, but I would also like to mention my other advisor, Jacques Finlay, in the Department of Ecology, Evolution, and Behavior, as well as my many other collaborators and gracious funding sources that have allowed this research to occur, including the Minnesota Water Research Fund. So my research has been focused on urban stormwater ponds. Here's one of many that you might have seen in the Twin Cities. But a lot of folks don't know, why are these here? What are they for? What are they supposed to be doing? And the short answer is there's a lot of stuff that comes off the urban environment when it rains. And we would rather that it not wind up in our lakes and streams if we can help it. So stormwater ponds are one of many green infrastructure ways that we can try to capture all of those pollutants and protect the water quality downstream of them. So a well-functioning and maintained stormwater pond should behave in this way, that the stormwater runoff, including lots of pollutants and nutrients, comes in during an event. Phosphorus in particular, which is the focus of my study, we're hoping that it settles to the bottom and stays put there in the sediments. And so the water that flows out the other end is much cleaner and doesn't have these pollutants and contaminants. Now, as we look at stormwater ponds, and these are just pictures of some of the many that I've been studying in the past couple of years, we see that they come in all different shapes, sizes, colors, levels of eutrophication. And, we start to wonder, why are some one way versus another? And how can we tell which ones are behaving properly and which ones aren't? So when we take a closer look at some of them, we can see that they're obviously doing a great job of capturing nitrogen and phosphorus. There's so much biological growth happening in this pond. But things become more complicated once you examine it in the context of the broader urban hydrology sphere. So water is moving around in many complex ways in an urban environment. And so what's happening in a pond, it's not enough for it to just accumulate nutrients, but we have to see, well, where are those nutrients going? And in some ponds, and increasingly so, we're finding that the phosphorus doesn't stay put in the sediments as we would want, but in some cases it's released back into the water in what's called internal phosphorus loading. And then when it rains, some of that gets pushed downstream. So we can have pea soup and harmful algal blooms downstream in the lakes we're trying to protect. So that's a big problem for Minnesota. And we've seen this happening all over the country. Here's a picture from Lake Erie near Toledo, Ohio, which had one of the most famous harmful algal blooms. The city of Toledo actually had to shut down its municipal water supply because neurotoxins were coming in. So it's a serious problem. But also within the ponds themselves, we can have these harmful algal blooms. And we've seen multiple instances around the country where there was a harmful algal bloom, the pond was pea soup green, and dogs were dying because they drank this water unknowingly. So I should put a bit of information here. People always wonder, well, my pond is green, could that be algae? So most of the pictures I've shown of the ponds look like this picture on the left, which would be duckweed. So that's actually a floating macrophyte. It's not an algae at all. In small concentrations, it's pretty beneficial. It's a good thing to have in your pond, but sometimes it can take over and make a thick mat. But again, it's not algae. It's not going to kill your dog. This middle picture is filamentous algae, which is more of a nuisance, but again, it's not releasing neurotoxins. And the one on the right is cyanobacteria. So that can be the harmful algal blooms, and that certainly can release harmful neurotoxins. So for that reason, I don't recommend you trying what is shown in that picture because it might irritate your skin as well. So the question is, why does this happen? Why are some of our ponds behaving in this way instead of capturing the nutrients as we want? There's much more detail on this if you want to read the full study that we published. This is a freely available paper online. I can send you a copy if you send me an email, but I'll try to cover some of the highlights today. So in the study, we took a closer look at 7 stormwater ponds. We tried to get a variety of shapes, sizes, and colors and ages to get a better understanding of what's going on. The first thing we did was we went out with a canoe onto these ponds. We put this plastic tube down. It's basically the same process as if you stick a straw in a milkshake and put your thumb over the straw and pull it back up. You can pull the milkshake back up with it. So we're capturing an intact sediment core as well as the water above it. We take that back to St. Anthony Falls lab and we can control how much oxygen is present in the water and also measure how much phosphorus is coming out of the sediments. And that's what this data looks like. I know it's a lot at once, but basically on this left plot, we're looking at the phosphorus release over time. The middle plot is showing dissolved oxygen being consumed over time. And on the right is a quantification of those rates. So what I want to point out is that we have different rates at which these things are occurring. In particular, ponds A, B, and E, which here are orange, yellow, and black. We see very high phosphorus release rates and very sharp consumption of oxygen right at the beginning of the incubation. So we wanted to figure out what is special about these ponds. Why are they releasing so much more phosphorus than the others? To get a better understanding of what's going on in the sediments, we did this very involved sequential sediment extraction process that can help us understand what forms phosphorus is bound to in the sediments. And in particular, the traditional thinking behind phosphorus in stormwater ponds and lakes is that iron is going to be the controlling element. So if you go back to your periodic table of elements, you remember that there's a 2+ and a 3+ on top of the iron. And that has to do with the oxidation state of the iron. So when iron is oxic, when it's in the presence of sufficient dissolved oxygen, it's going to be in the 3+ charge. And if you look at this chemical equation, you can see that that fits pretty nicely with phosphate, the PO4 3-. So those two bind together and settle into the sediments. And you see oxic sediments, we have that kind of orange rust color. If there's not enough oxygen in the pond, then iron is going to be in the reduced form under anoxic conditions, which means it has a 2+ charge, and that no longer matches with the phosphate 3-. So those two separate and dissolve back into the water. So that's when we have phosphorus being released. Now, when we looked at our ponds, here we're looking at the iron-bound fraction in purple, and we see that A, B, and E, the ones that had the most phosphorus release, do have pretty high iron-bound phosphorus that would be susceptible to low oxygen. But we also see that they had really high labile organic bound phosphorus, which is sensitive to microbial activity. And so thinking of both of those together, we consider them mobile phosphorus. It's the phosphorus that is most likely to be easily mobilized. And when we compared the concentrations in the sediments to the release rates we actually found a pretty good relationship for mobile phosphorus. So that's one way that we can start to quantify which ponds are susceptible to this phosphorus release. More recently, my collaborators have done some research looking at a much larger data set of about 20 stormwater ponds, and we can see that these relationships are holding up, which is exciting. We're also seeing that there's a strong relationship with the sediment organic content in general, which is much easier and cheaper to analyze. So if we can get a reliable relationship there, that'll be much easier to assess ponds for vulnerability. So now we know what happens and why it happens, but when does this actually occur in the field? Under what conditions does the stormwater pond begin to release this phosphorus? So first I wanted to mention some of the design assumptions that go into these stormwater ponds. Of course, there was the assumption that they would indefinitely be able to store phosphorus in the sediments, and we've seen that that isn't true. Under certain conditions, the phosphorus begins to be released. So other assumptions were that these ponds would be pretty shallow. That is usually the case. That because of that, they would be well mixed by wind and storm flow events, and that they would at worst destratify daily. Maybe it heats up during the day and stratifies, but then at night it should cool and turn over and let oxygen back down to the sediments. So we've been monitoring some ponds in the field to see whether these assumptions hold true. So one of the simplest and cheapest ways to assess stratification that I found is what you see a picture of there on the left. So that's a PVC pipe. Each of those blue dots is a temperature pendant. So at a specific depth is just measuring the temperature continuously. And the black cylinder is a dissolved oxygen probe. Here in the middle, we see what some of that data looks like. So you see those blue lines, gradients of blue lines. Each of those is representing a depth in the water column, and we see what the temperature is. So in the fall, you can see that those lines are pretty close together. We have the water pretty mixed, and the temperatures are consistent. And then you can see going into the winter, as the ice forms, you start getting stratification with different temperatures at different layers. So it's a pretty visual way to assess that. And in green, you can see the dissolved oxygen response. So when the water column is mixed, you see dissolved oxygen moving up and down. But as the water begins to stratify and there's ice across the surface, you see that dissolved oxygen plummets and there's not really any oxygen in the pond. Now, if we zoom into the summer, we were talking about it might heat up during the day and cause a pond to stratify, but at night we would expect it to cool. Well, having done this temperatures data collection, we can see that heating and cooling definitely occurs, but it's most pronounced just in the surface layer of the water column. And as we look at the deeper layers, these darker blue colors, there's not much evidence of that at all. So although there is heating and cooling happening over the course of the day, it doesn't seem to be enough cooling at night to de-stratify the pond. So this pond was consistently stratified during this period. The other thought about mixing a pond might be that if we have a large storm flow, maybe that can just flush out the entire pond and bring in new water. So this red line indicates when we had a 1-inch storm event, which is on the larger side of your typical storm events. And we see that indeed it was noticed by the pond, cool temperatures came in of water, but we see that it really still only happened in the surface layers. And if you look at the bottom three or four layers, the temperature didn't really shift at all. And what that tells us is most likely the storm flow skimmed across the top of the pond, displaced some of the water, but not all of it. So that has serious implications when we're trying to calculate what the residence time is, how long that storm flow is going to be in the pond to receive treatment. And it may not be what we're expecting. So we definitely wanted to take a closer look at that and understand why that might be. And one of the big factors we found is that in Minnesota specifically, we have quite a bit of chloride going into these ponds. Anyone who's driven during the winter could attest to that. So what we see, this is kind of an interpolated version of those data that I was just showing. So on the top plot, we're looking at temperature data interpolated across an entire year. In the middle, we're looking at dissolved oxygen in a pond. And at the bottom, we're looking at the chloride, at salt, measured as specific conductivity. So we can see that during the winter, at the beginning of the year, temperature is very stratified because we have ice at the top of the pond. Coming down into the spring and summer, especially in the spring, we see with the snow melt, a lot of the electrical conductivity really goes up in these ponds, but that lingers into the beginning of fall even, which was surprising. We would have assumed that the salt water would just get flushed out with the first couple of storms, but we see that that dense salt layer really lingers and contributes to the stratification in the pond. Of course, we see dissolved oxygen responding accordingly. So as the pond is stratified because of temperature and chloride, there's no oxygen at the bottom, which is what you see in the bright red. Come summer, we have strong thermal stratification, as I had shown before. In the fall, the chlorides have finally been flushed out, and we see the thermal stratification dissipate. So the pond is allowed to mix, and we see dissolved oxygen at the bottom. But then winter begins again. There's ice and there's stratification because of that. So we go from assuming that a shallow stormwater pond is going to be well mixed and aerated throughout the entire year. And in reality for this pond, as far as we can tell, it was only aerobic and mixed for about 1 month out of the year. So quite different conditions that could promote sediment phosphorus release. I also wanted to show some more recent research that has been done by my collaborators that's starting to look at the presence of duckweed. So before we talked about when a pond has a lot of phosphorus, duckweed could be an indicator, but they're starting to find that the correlation is so strong that perhaps the duckweed is driving some of the sediment phosphorus release by creating a barrier that prevents wind mixing and dissolved oxygen diffusion into the pond. So more on that to come. So what can we do? We've got all these ponds. They're supposed to be protecting our lakes, and we find that over time, it seems like a lot of them stop doing that. It's very expensive to get rid of a pond. So what can we do instead? We did a modeling study recently using C=W2, which is a lake and reservoir model developed by the US Army Corps of Engineers. And we used it to model 4 of our ponds in pretty high detail. So we have all of our bathymetry and the shapes of the ponds, and we modified the water quality parameters to see how each of them would behave. And our goal was to evaluate some of these potential remediation strategies that we could use to put more dissolved oxygen into a pond, to stop the phosphorus from being released. And I wanted to highlight the 3 that our research suggests might be the most effective. So watershed-based methods, chemical treatment of sediments, and mechanical aeration. So for watershed-based methods, that includes preventing all of this organic matter and phosphorus from entering your stormwater ponds. There's a lot of research coming out of the U that suggests that street sweeping is a very cost-effective way to do that. Similarly, you might install other green infrastructure practices in the watershed and just decrease the amount of water entering your pond and filter some of that water and just decrease the overall pollutant load entering a pond so they don't have to deal with as much. And we go into a lot of detail about establishing the cost effectiveness of that, which I don't have time to cover today, but happy to go into it in the question and answer. But basically, we see that in the original case, which we have here in blue, on the left plot, I'm looking at impact on total phosphorus export, so the ability of the pond to retain the phosphorus. And on the right, we're looking at impact on the total phosphorus concentration in the pond itself. And we see that the volume reduction definitely reduced how much phosphorus is getting out of the pond because less water is getting out of the pond. But when we look at concentration, it increases a bit because you have less water diluting the phosphorus in the pond. So that starts to raise questions of what are you managing a pond for? Is it just to protect the lake downstream, or is it seen as an amenity by the residents adjacent to it, and you need to worry about the water quality in the pond itself? So that's a serious question that managers have to consider in deciding what approaches they want to use. Then we looked at chemical treatment of sediments. In lakes, this is usually done as an alum application. You go out with this barge and release an aluminum compound that can bind the phosphorus in a more permanent way. At the bottom pictures are showing a smaller scale version that's being pioneered here in Minnesota for applying it to ponds. And here at the U, we're also studying whether we can use iron filings as a cheaper alternative. So these are basically shavings from old cars. And we're finding that as we apply more iron into a pond, it gets to a level where it precipitates chemically. So you can get that phosphorus trapped in the sediments independent of oxygen. And looking at our additional data set of 20 ponds that my collaborators are working on, we're also finding that ponds that have more phosphorus in the sediments already seem to be releasing less phosphorus to begin with. So that we're excited to be moving in this direction with the research to see if we can find more tools. I see that I'm running out of time, so I'll skip ahead with the results. But anyway, we see that there are reductions in the phosphorus that's being released based on our model. We also looked at mechanical aeration. The main point I want to make here is that mechanical aeration means a distributed system of bubblers across the bottom of the pond. So you can think something like a wastewater treatment plant, and that's to mechanically mix the pond. It is not an ornamental fountain at the surface of the pond because the amount of water going into that is very limited. It's only taking water off the surface in most cases over a very narrow footprint, and it's spending most of the energy pushing that water into the air rather than mixing the water column. So this technology has been around for a while. You want to make sure if you use it that it's being installed correctly and you're not resuspending sediments, because then you might actually create a worse problem for yourself. And again, all of our data. Oh, and one more. So this is for those remediation techniques that I mentioned. This is what the numbers break down to for cost effectiveness. So if anyone is curious about what it would cost to do this to a pond, here's some ballpark numbers based on the ponds we modeled. Of course, it's going to be different for the ponds that you work with, but maybe a starting point for your considerations. And with that, thank you very much. And I look forward to talking with everyone about this.
Vinny, thank you so much. We appreciate your presentation. There's a lot of practical application happening here, and we've got some questions coming in through the chat. So Vinny will be able to answer questions. If John Gulliver, if you'd like to turn on your camera and be ready to take a few questions as well, that would be great. Same with you, Bernie. Why don't we go ahead and I'll just get started with some questions that are in the Q&A right now. This first question, Vinny and John, is coming in from Ross Bintner. And he says, can you confirm that all stormwater ponds in these studies are actually designed and constructed in upland and part of a Minnesota MS4 with a known maintenance history, and not a natural water body that receives stormwater? It says a lot of the pond picture looks like receiving waters. Vinny, do you want to take that one?
No, I'll take it.
Okay, thanks, John.
So, yeah. What we should have said in the title, we just shortened it to stormwater ponds to generally give people the idea that that's what we're working on. What we should have done was say ponds that treat stormwater, which qualifies for all those ponds. So there's a difference between stormwater ponds and ponds that treat stormwater. And the difference would be a stormwater pond is an upland pond where you don't have a prior wetland there. You have no wetland regulations governing you. And so you can do what you want with it. You can maintain it any way you want. But there are also ponds, former wetlands that treat stormwater. They've been dredged out. They've been piped with stormwater. They have stormwater input coming into them. But they are also considered a wetland, and they need to meet wetland regulations. And so you are definitely constrained in what you can do to these ponds. And I recognize the difference. I'd like to apologize to Ross because we shortened the title to stormwater ponds instead of ponds that treat stormwater.
Thanks, John. Okay, next question's coming in from Bill Selbig. He says, is the age of the pond an important parameter to determine P export potential, or is it more a function of the accumulation rate of sediment from the contributing area?
Yeah, it's a great question. That's definitely something we thought would be more important than what we found it to be. And I think that's for a number of reasons. So there is clearly a difference in behavior from a newly constructed pond that for the most part has mineral sediments, perhaps has a clay liner at the bottom and doesn't have that organic phosphorus rich sediment. You clearly see less phosphorus release. But as a pond begins to age, very quickly you get an accumulation of this organic matter coming in off the watershed. And it seems like it doesn't matter so much how deep that layer is, whether this pond is 5, 10 years old, 40 years old. It seems to cross a threshold at a certain point, and then that's characteristic of what the sediments are. Other changes we've observed over time is that the vegetation around a pond matures, so the exposure to wind mixing changes, and the pond may certainly get shallower as sediments accumulate. So there are a number of changes in the behavior, but we haven't been able to identify anything as a clear threshold or a sort of a predictive identifier. Although my collaborators and Jacques Finlay in particular are still looking at that, and they're hopeful they'll be able to identify something. I don't know if you want to add anything, John.
No, that was good.
Thanks, Vinny. This question is about the adding of iron filings. The question is, if you add iron filings, couldn't that push you over the limit for the iron benchmark for stormwater, thus creating a new problem?
I'm less familiar with this research because Dr. Purnima Natarajan is the lead investigator on that topic. So John, perhaps you can answer this question.
All right. Yeah, the limit for drinking water is 1 milligram per liter, which is fairly high concentration. And we haven't really seen the concentrations of iron in the ponds reaching that level, but we were concerned about that. And that would be both for, there's a 1 milligram per liter concentration limit for biological and for drinking water concerns. But we didn't see that. It was higher, but not that much higher.
Thanks, John. I see a question coming in from Mark Willett, who asks, have you looked for a biological resolution for the management of phosphorus?
Absolutely. We're open to any kind of resolution and different tools that we could apply. I don't believe that we investigated any of those in particular. In algae management, I remember I was doing a project in one of my classes looking at decreasing the amount of filamentous algae in a pond as a result of high phosphorus. And we found that barley straw is a biological or more natural way of potentially suppressing that algae growth, but it wasn't directly addressing the phosphorus. Perhaps John is more familiar with other biological tools.
The only thing that you can do is keep the phosphorus in the sediments, because phosphorus doesn't disappear. When you have floating algae and things like that in your pond, like duckweed, that can be a way of biologically treating the phosphorus by capturing the phosphorus, and then you have the pond maintain that by putting some sort of barrier to the duckweed from leaving, and then the duckweed eventually would settle to the bottom and take the phosphorus to the bottom. So that would be a biological treatment, but we're doing that now. We have plenty of duckweed in our ponds.
Thank you. A couple of people in the Q&A have a question about what can a homeowner on a pond do?
We get that question a lot. We get a lot of really enthusiastic homeowners come out when I'm out with a canoe in the pond, and they've told me a lot of things that they've tried. They've tried applying algicides or other things to kill off the duckweed, and it seems like that's pretty limited. It may have some adverse impacts to the fish and other things that they would like to see in the ponds. The most cost-effective strategy in any case is always going to be prevention. So if you have a small controlled watershed within your neighborhood, if you can be very diligent about making sure that leaves don't wind up in the pond, picking up after your dog, not applying fertilizer, which in Minnesota usually doesn't include phosphorus anymore in domestic applications, thankfully. But if you can prevent all of that from accumulating in the pond, it's going to be in better shape. Once the pond accumulates this source of phosphorus in the sediments, it's a lot more complicated. Then you're into these more expensive treatments like alum and some of the tools that I mentioned.
Okay, thank you. It doesn't surprise me that you get that question a lot. And as someone who has a pond nearby, I'm listening myself for your tips. So thank you. Taking us in a different direction, this question is coming from Craig Fairbaugh. Craig asks, the stratification issues appear to be linked to cold winters and chloride loading. Do you expect similar stratification issues and P export in climates with warmer winters and less chloride loading?
That's a very interesting question, and it's something I would like to research in the future. So I'm originally from North Carolina, and that's where I'm going back as I finish my program. So I would love to see, do North Carolina ponds behave in the same way? My expectation would be that without the pronounced cold winter of Minnesota, and certainly without the thick, persistent ice layer, that they should be more mixed in the winter. But yeah, I don't have the data to see yet whether that's the case.
But they would still get stratified in the summer when most
Correct.
of the problems occur.
Yes, and that could be even worse in the warm climate. Thanks, John.
Thanks, Vinny and John. Our next question is from Emily, who asks, do the ponds that perform worse than others still fall within the recommended maximum minimum average pond depth as recommended by the MPCA? Is there any correlation between meeting those recommended guidelines and the performance?
Yeah, that's a very interesting question. And I don't believe that we've found an easy answer to it. It seems that ponds really are, if you study one pond, you've studied one pond. There's a lot of contributing factors to it. In general, we've seen that most of the ponds we're looking at are between 0.5 meter deep to 3 meters deep. I would say 2 meters is about the average. The recommendations I've seen are to keep it at least 1 meter deep, I believe, so that you're not getting emergent vegetation. Then you wind up with something like a wetland. In terms of phosphorus, I don't know yet whether that transition from pond to wetland is a good thing or a bad thing. It's a very complex topic. But a lot of the early recommendations for these ponds, and certainly when they were first being built by the NURP program, the National Urban Runoff Program, they were saying that the ponds could be as deep as 10 meters to prevent stratification. They considered that to be a shallow pond because they were using data from lakes, which are much, much deeper. But based on the strong stratification that we've seen, even in ponds that are 1 meter deep, I would not recommend that a pond be that deep. Although, since we haven't studied it, it's always possible that there's something else, and maybe you cross a threshold where things stop happening because you wind up with the lake instead of a pond.
Thanks, Vinny. We have a question from Brett Emmons, and a couple of folks have indicated interest in hearing your response to this. If pond mixing via wind is considered key to mixing/introducing oxygen, with wastewater aeration as an example, it sounds energy intensive with commensurate costs and CO2 emissions. Has anyone considered using small scale wind turbines and/or solar as the energy source to power pond mixing?
Yep, there are quite a number of private suppliers of these mixing devices. Some of them are solar powered, some of them are I don't think I've seen one with wind turbines, but a lot of them are solar powered, which helps you install these on ponds that are a little remote and you don't have the energy grid. Ultimately, I think the energy source is secondary to the design of the system. As long as you've properly installed this, you have sufficient aeration to mix it, it should be effective. But yeah, we're always looking for ways to include green energy into these systems so that it's healthy. We're also curious about whether we might be able to promote wind mixing just in the design of the pond, if we make them large enough that the wind can cross the surface, if we can manage the vegetation on the banks to allow, potentially not a treeless state, although, native prairie is what's typical in this region. Perhaps we could encourage that around ponds, but otherwise maybe you can preserve a corridor for the wind to move through, similar to what we do with the electrical lines, but along the direction of the prevailing winds. Sadly, we don't have all of the data that we need to make that recommendation, but it is something we're interested in studying.
That sounds fascinating. Thank you. We have a question coming in from Elliot Mergen, and some other folks have also indicated interest in hearing about how do chlorides increase stratification?
Great question. So the main part of it is it's not really important that it's chloride, it's that there's something in this water. And so the water is going to be more dense, right? Like salt water is denser than seawater. So that means when you get stratification, that's a density gradient. So thermal stratification is that the hot water is less dense than the cold water. So cold water sinks to the bottom, hot water rises to the top. And that difference in density resists mixing because the hot water is trying to stay here, the cold water is trying to stay there. And so they're not interacting as much as if it were all one temperature. With chloride, or you can see this with sediment and turbidity, there's just a denser water at the bottom and a less dense water at the top. So the salt water at the bottom is trying to stay at the bottom and it doesn't allow it to mix as much.
Okay, next question is from Carolyn Dindorf, and she says, most fertilizers use potassium chloride as the source of potassium. Have you considered this as a source?
As a source of chloride? Yeah, I think it could certainly be a contributor to it. I don't have specific data on this, so John, stop me if I'm way off, but my hunch would be that the amount of chloride being applied as fertilizer, particularly in domestic applications or residential applications as opposed to agriculture, is going to be much, much less than what's usually being put onto streets and driveways in terms of de-icing. So I still think that that's the primary concern, but it could certainly be a contributor.
Yeah, I think that's true. I think Carolyn knows that the quantity of salt of sodium chloride that we put down every winter to melt ice is just tremendous. And it might impact, the potassium chloride might impact farms where they're putting in a potassium chloride, but I don't see it as being a big impact compared to road salt in the cities.
Thanks, John. This question comes to us from Amy Regal. And Amy says, hold on, it just disappeared. There we go. Are there additional resources on aerators or bubblers that you would recommend for decision makers, such as cities, homeowner associations, property managers? Is more research being done to refine implementation of these practices?
Great question. And that was something we were looking at the beginning of our model study, if we could find some good data out there to inform our model. Unfortunately, it seems like most of the data related to mixing is from lakes and reservoirs, which are quite different from these shallow stormwater ponds. We have a number of case studies and anecdotal reports from practitioners having applied this in stormwater ponds with varying levels of success, but there wasn't much numerical data to inform it. So with our simulation, we made some assumptions about what the reported improvements to water quality would be from aeration, but we weren't able to mechanistically model the actual act of the mixing. This model C = W2 has listed that as one of their priorities for future development, but it hasn't been implemented yet. So I don't have those answers, but if you're able to find a source, I would love to read it.
But we did take information from people who install these, right?
Yes, sorry. If you look in our report, we have information that could help with the design of one if you determine that it would be helpful to you in terms of deciding how many aerators you need in a pond, because it's quite different than a reservoir. Reservoirs tend to be much deeper than they are wide, so you can get away with a couple of bubblers, and as the column rises, it'll mix the entire water column. Pond being only 1 meter deep, but maybe 100 meters across, you're going to need much more aerators in order to mix the water column. So we provided some guidance from a practitioner as well as some cost estimates based on some calculations we did from one of their suppliers.
Okay, let me just, I had a question here that came in from Shanna Kent. She says, trying to think of improving future practices, is there a better alternative to ponds? Should ponds be phased out? Would many of these findings also transfer over to rural settings? Are regulators also aware of this and looking into design modification or alternatives?
These are all great questions and definitely something that we hope will come out of this research. Unfortunately, it's going to extend beyond my PhD because it's just such a complicated question. But I'll try to get at some of the things that we've been seeing. So in particular, whether this relates to agricultural settings, I think in terms of internal phosphorus loading, that is something that's been observed. There's certainly quite a bit of phosphorus going into these ponds in agricultural settings. As we mentioned before, the chloride sources may be quite different, so you don't see the stratification from that reason, but certainly from thermal stratification. So harmful algal blooms in ponds, I believe, would still happen in agricultural settings. As opposed to whether folks should be building ponds or not, that is being driven, I think, by a more economical factor. So in Minnesota, we've identified that these stormwater ponds over time accumulate, in addition to phosphorus, heavy metals and, sorry, I'm blanking on the acronym, John, the polycyclic aromatic hydrocarbons. So these are carcinogenic substances related to the coal ash sealants that we put on asphalt driveways. I think they've changed what they're composed of now, but a lot of these materials have accumulated in our ponds, basically to the point that if you dredge a pond, you're required to test the sediments to see the concentration of these substances. And if it's high enough, you actually have to treat all of the sediments that you dredge from a pond as hazardous waste and send it to a lined landfill, which is much, much more expensive than if you could just apply it on an agricultural field. So for that reason, ponds aren't usually being maintained as frequently as they need to, or it's just cost prohibitive in general. So folks are shying away from ponds for that reason.
But the existing ponds, many of them, probably most of them, still treat for water quality, and they are still valuable to do things like take care of the changes that adapt to the changes that we are envisioning with climate change. So I think that ponds are still a good thing. It's just the way we maintain them. We've discovered this problem that many ponds have, not all ponds, but many ponds. And we've discovered this, and we need to determine ways to take care of it, ways to maintain these. It's been, 50 years since we started building ponds, and we never really looked at what the ponds did until recently.
This is why your work is important, the two of you and your whole research team. I'm just checking our time. We're at about 12:23. How about if we take one more question and then we'll get ready to wrap things up. This question is coming from James Sherrard, who has a specific question about your research. Does your research provide an updated estimate regarding the annual phosphorus reduction from shallow cold weather ponds?
Not specifically. I'm not quite sure I'm familiar with the context this is asking about. Do you know, John?
I was thinking maybe it's a kind of a global type thing. We're more specific. Our research is more specific on individual ponds and not globally covering all ponds. We may be able to put something together with some rationalizations, but we haven't really thought about that.
Okay, thank you. You know what? That was a quick answer. So I'm going to take, this is, I promise now, last question. So this is a sort of a comment or question. Oh, thank you, Vinny, for sharing the modeling report as well. Absolutely. This is coming from Mike Trojan, who says, this might be more of a comment than a question, but historically ponds have been designed for rate and sediment control. If we were to start designing or retrofitting ponds for phosphorus control, it would seem that design standards and guidance need to change. What would you say about that?
I think so. And that's part of one of our ongoing research projects is to make those new recommendations for how we might design and maintain ponds specifically with phosphorus in mind. And I suspect they'll continue to change as the research progresses, because we still have many more ideas of things to look at and to try.
Okay, well, that wraps up our Q&A. And Vinny and John, we want to thank you so much for your expertise, for taking the time to share it with us. As we mentioned, we'll make sure that you all get copies of the report that Vinny mentioned. You will also receive, all of our participants will receive this recording, so you can revisit the information, and we encourage you to share it with others. And before we wrap up today, then, I'd like to turn things over to our Minnesota Water Research Fund Vice Chair, Michelle Stockness. And we are just so grateful to Michelle for all of her thought leadership and her engagement with us on the advisory committee for Minnesota Water Research Fund. I'll tell you a little bit about Michelle. She received her bachelor's in civil engineering from the University of Missouri-Columbia, and she is vice president at Bar Engineering, where she specializes in water and wastewater engineering, and she approaches her projects with a sustainability emphasis, specifically focusing on infrastructure rehabilitation and green infrastructure. Michelle's work involves managing, designing, and administering construction for water supply wells and pump houses, pumping stations, water and wastewater treatment systems, water storage and water distribution and collection systems, and water reuse. We are also excited to say that Michelle was recently elected to serve as vice president for the American Water Works Association. As an AWWA member for more than 16 years, Michelle also serves as a member of the organization's Diversity and Member Inclusion Committee, and she is an active member of AWWA's Minnesota section. Thanks so much for all you do, Michelle. Take it away.
Yeah, thanks for that, Shannon. Thanks, Vinny and Dr. Gulliver, for that presentation. Obviously, this was a hot topic, and there's a lot of questions and engagement around this. And I want to say this is a great example of what we're trying to do with this Water Research Fund. We're trying to fund projects that are helpful to the water industry, try to fund innovative work, and then we want to try to have a venue to share this work with you all to get that information and research out there so that you can use it in your work. So it also, I think, points to the really strong stormwater community we have in Minnesota, which is not the same everywhere. So thanks for that awesome presentation. And you guys know how to get a hold of them later if you have more questions. And I wanted to thank all of you for joining us at this presentation today. This is what we're trying to do, and you know a little bit more about us, and we're trying to advance the water industry and water research in Minnesota. And I support them by being on the advisory committee and being a vice chair, because I think building a stronger water community in Minnesota is really important to help keep improving the state of the water industry and also the water workforce. Water is getting more challenging every year in everything we do. So we need more help and more research to keep up to date. So we hope you all are inspired to help us out at the Water Research Fund a little bit more. And I wanted to share a few ways that you can help get more connected with us. So first of all, you can join the mailing list. Shannon put it up there. And you can also go on our website and you can get connected to the mailing list, and you'll get invites for all our future presentations that we're going to be doing. Secondly, we would love to hear your ideas and thoughts about what research you want to see, what's important to you, what you want to know more about. We're funding projects every year, so your input is super valuable to know what we need to do more to help you. So please share your ideas at any time. Especially on kind of what research that would help you. I think that would be really helpful. We're trying to be a connection between U of M and the larger water industry too. Also, so that's a few ways you can connect with us. Another way to connect with us is financially, of course. Nothing is for free. Everything costs money, and we're always looking for more funding to support more research with this fund. So a few ways that you can contribute financially, of course, it's Give to the Max Day. You've probably gotten 1,000 emails about that for next week already. So put this one at the top of your list. We'd love to have some funding with you from you for Give to the Max Day. And a new thing we're doing this year, we just started this and we'll roll this out more, but we're starting a new partnership program for companies and industry partners, $500, $1,000, $2,500. We'll roll out a little bit more on how these partnerships can benefit U of M, and they can benefit you and your company. So if you're making budgets for next year, we'd love if you could put that in your line item budget for supporting this fund for next year. And like I said, Give to the Max Day is on November 17th, next Thursday. We'd love if you could donate to this fund. We're trying to raise at least $5,000 on Give to the Max Day for this fund to support. And Bernie is super generous with his knowledge and his time and his finances for this. And he said he's going to match anything for the first $5,000. So if we could get to that, we can double the money coming into this one. So that'd be really great. So again, thanks to you all. Thanks for your time. Thanks for supporting U of M and water research. And have a wonderful afternoon. And we hope to see more of you at future events. Thank you so much.